What tasks from the previous homework we need to discuss?
Maybe the 4 and 5.
Why 1 and 5? Yes?
4 and 5.
4 and 5. Okay. So let's see this form. Okay. Oh, 4 is large. So for A, B, C, yes?
B and C maybe.
B, C,
Okay.
and 5, yes? To discuss.
Yes.
Okay.
Yes.
Okay. For A, answer no. Is not pre-compact. Example from our seminar, fnx, for example, xn on in this space, or x minus a over b minus a powered n in CAB. It's just Fn transformation, so that doesn't matter. Yes, of course, we know that all Fn at 0 equals to 0, so it is exist constant C1 that Fn 0 less than C1. Yes, and these functions are monotonic, so Fn derivative equals to Fn1 minus Fn0 equals to 1, so they exist constant C2, such that integral 0, 1 Fn prime dx less than C2, yes. And on the arbitrary interval AB, you can consider such family. So all conditions fulfilled, yes, but this family Fn is not equicontinuous. I need to solve B because I will show that C is a partial situation of B. So let's consider for B. For B, we have M2 function from FC1. There exist constant C1, C2, that's such that FA less than C1, and the derivatives are bounded in the sense of L2, yes? This set. First, boundness, yes? Boundness. Boundness of M2. We know that f of x equals ax f prime t dt by Newton-Leibniz formula plus fa. Then fx less than ax f t dt plus absolute value f of a less or equal whole integral from a to b f prime t dt plus c1, and then Hölder or Cauchy-Bonnikovsky inequality, and we show that this is less than ab the square of derivative 1 over 2 square root b minus a plus c1, so it is less than square root c2 b minus a plus c1, yes, and equicontinuous. equicontinuity. Let x minus y less than delta. We know that fx minus fy equals ft dt from y to x. It is less than, I don't know the order of x and y, so I must write the out absolute values, preserve it, and take absolute values of integrated function, and then use again Cauchy-Bunyakovsky inequality. Cauchy-Bunyakovsky inequality less than ft prime square dt from y to x, here modulus and 1 over 2, and square root of x minus y, yes, by Cauchy-Bunyakovsky inequality. Then we see that it is less than square root from C2 on square root x minus y. So we have a small oscillation of function, so it is equicontinuous. So we conclude that M2 is precompact. Is precompact. And for C, the space, the set M third is a function of FC1 AB such that so-called the ellipsoid in space of continuous functions. Pt less than C. Shows that M3 lies in M2 for some constants. C1 and C2. Is this idea is clear? It is idea of the proof. And then we conclude that M3 is precompact too. So it is idea. Let's do it. Again, fx, it is by Newton-Leibniz. Fa, yes. Then I can write that Fa equals to Ax integral of derivative minus function f of x. So we show that f of a, the absolute value less or equal of integral plus absolute of functions. Then integrate or AB. Then not this integrate, but we can continue our estimation. I large this integrate over interval and integrate this. Here this is constant. B the value of function f in A, it is a constant. So we obtain on the left side this, and here we obtain again it is a constant. So b minus a, ab, and integral of derivative dt plus this integral. Okay, and then use Cauchy-Bunyakovsky. So it is less than b minus a square root of b minus a b f t square dt and powered 1 over 2. And Cauchy-Bonnikovsky for the second integral. So again, square root b minus a b, and the integral of the square of the function. So you see that f of a less or equal square root b minus a multiplied on square root c plus square root c divided by square root of b minus. So this condition we fulfill, yes? And so f of a is bounded. So and then what we need to show, we must show that our derivative is bounded in the sense of L2. Yes, we must show that our derivative is bounded from L2. So we see that from this formula, again, Newton-Leibniz formula show us that f t dt equals f of x plus f of a. Let's define this as C1. Yes, this is C1, this new constant C1. And then okay, so just M2 we have but we need to do anything from definition of M3. We need, this is finished because by definition of M3 of M3 we have this inequality. Yes. And we immediately obtain that this is true too. Yes? So we show that M3 is lies in some M2 with some constant. For example, we need only to show the boundness of uniformly boundness at point A. Yes? It's sufficient. So M3 is precompact. Is it clear?
Yes, yes.
Okay. And 5, yes? What 5 problem was? Let's see what problem 5 was. That unit ball from L2, yeah. Is not precompact. In L1. Do I need to show that L2 is embedding in L1? Or it is clear?
Not very clear.
Not
We can
clear.
show it.
Okay, let f is from L2, and let's check its norm in L1. Again, by Cauchy-Bunyakovsky, Euler inequality, I consider that it is multiplicated on 1, so it is less than ft squared dt square root 1 multiplicated on the same integral. Just I in details write what I use in previous task. Yes, 0, 1. It's just the norm of f in L2 because it is equals to 1. So we see that the norm of f in L1 less or equal the norm of f in L2. So function f is in L1. Okay, and now let's consider such functions fn. Oh, I consider the countable set of n1. Let's n1. We construct two functions. f11. It's a characteristic function 0, 1, 2 minus characteristic function 1, 1. By graphics, it is here 1 and here minus 1. But here open, yes, for example. Then for n2, I think I tried one on this. For arbitrary n, what we construct? x1, I divide it on subintervals. Subinterval, it is y. Doesn't matter, the 1 minus 1. So the length of all intervals is 1 divided on nth power of 2. And function looks like here 1, here minus 1, here 1, here minus 1, 1, minus 1, 1, minus 1, etc. Yeah, clear? What you can say about the norm of these functions in L2 and in L1? If you take the absolute value of the function equals to 1. Yes? Then the norm of all these functions in L2 and L1 equals to 1. But what you can say about the norm of of the difference of the functions in L1? When you go to the next step, yes. So you have the interval of the length 1 over 2n. Then you divide it on subintervals, yes. And again, new functions here 1, here minus 1, here 1, here minus 1. And the previous function was here, for example, 1. Yes, previous function. So I consider picture when, for example, n less than greater than m, then the green function is fn, and the black is fn. and it is on each interval, yes? And where we have 1, then the function, the difference is equals to 0, yes? But when we have -1, the difference equals to 2. So it's easy to see that the norm of Fn minus Fm equals in L1 equals to 1. So there are no fundamental subsequence. Yes? Is it clear?
Yes.
Okay. So let's discuss some tasks, some examples of bounded operators and bounded functions now, and construct some sets of operators. Some sets of operators. First example. First task. Take alpha equals alpha 1, alpha 2, alpha n, and so on from L infinity, and define operator of multiplication alpha x, alpha 1 x1, alpha 2 x2, diagonal operator, alpha n xn, and so on. Let's consider it in L2. You can consider it in any LP in L2. Find the norm. Find the norm. Let's, because we work in L2, I find the estimations for the square of the norm for short writings, not to write the square roots. So by definition, it is such sum. How you can estimate it? What you can take away from the sum? We need to obtain just the norm of element x. So we must take away the alpha k. How we can do it? For example, you can do it. What you can take? The supremum of alpha k square in for any k, and then we obtain just the sum only for xk. Yes. If this estimation is clear, so we obtain the norm of alpha in L infinity, multiplicated square, and multiplicated on the square of the norm of x in L2. Yes. So if we take supremum, so conjecture that the norm of operator not less from or equal to norm of sequence alpha in L infinity. Yes. And again, two situations. Situation A, they exist.
Sorry. Why the supremum of alpha exists?
I don't. I take alpha from L infinity.
Yes.
Beginning. I take alpha from L infinity. Supremum may not be exist, but I consider two situations. The supremum exists, and supremum is just a supremum. First situation, exists the index k0 such that module the absolute value of alpha k equals to the supremum. Then take x equals to 0, 0, signum alpha k0 on the k0 place, and other coordinates 0. Then ax, the norm in L2, just one coordinate, just alpha k0. Alpha k0, and we suppose that such index exists, such coordinate exists. And second situation, there are no such one index, it doesn't exist, but exists sequence Kn, which tends to the infinity, such that the absolute values of Kn tends to this supremum. By definition of supremum, such subsequence exists, yes? And then we need to take not one element, but we take sequence of elements xn, which looks like as follows. On the kn place, we take the corresponding signum of alpha kn. And other elements are zeros. And you can see that if you act by operator on this sequence and calculate the norm in L2, the norm of result, we obtain that it is just alpha k n, which tends to the zero, not to the zero, to supremum, to the norm of element alpha in L infinity. So by this we immediately obtain that the norm of this operator is just the norm of sequence alpha in L infinity. F capital, we check as following. For any f small continuous function, f capital acts on f as following. Find the norm. Find the norm. Again, beginning from the estimation. For arbitrary function f small, we can write it as the absolute value of this integral, or the difference of the integrals. Then triangle inequality for the absolute values. You can only, and then inequality for integrals. For integrals, when we put the absolute value inside the integral, we can obtain only the value which is not small. But here we have plus. And we know that in arbitrary space CAB, we have a very useful inequality. For any point t from AB, the value at point ft less or equal to the norm of the function in this space, because it is maximum. The norm is the maximum of values, and that just we have only one value at some point t. Yes. If we use this, so it is remark, because it is easy, but it is important. So this less than norm or equal. This is again less or equal to the norm. So our estimation that it is less or equal to norms. So what we can conclude? We can conclude that the norm of the functional less or equal to 2. Yes. And just let's analyze for what function we can obtain the equality. For what function we can obtain equality. Simple analyze. If we take function f of the form, for example, here 1, and here minus 1. Is 1, here minus 1, 1, minus 1. Then, of course, equals to 2. But what problem? Is what is the problem? Function f is not belongs this function. Let's take f0, f0, and here
It's not continuous, right?
Yes, yes, it is not continuous. But what we can do? Let's take small neighborhood of 0. Take n sufficiently small, large, that this neighborhood lies inside the interval, and construct the smooth version of our function. Smooth version. So by red, I picture the graph fn. I don't write the formula, you can do it, of course. But of course, this function is continuous, yes? Function fn is continuous. It is first property of this function. The norm of this function, fn maximum, equals to 1. So we work on the unit sphere. We work on the unit sphere. And, oh, sorry. And our functional acting on this sequence, it is just 2 minus over n, yes? Because it is double squares. It is square of this triangle plus square of this triangle. And the square of each triangle is 1 over 2n, but we have 2 triangles. So it is easy example when we can just calculate. For some problems, it is we do not need to find the precise value. You must only show that it is tends to the our number. Yes. So we then obtain for arbitrary function f, we obtain the estimation above by the number 2, and we construct the sequence of functions fn, for which we can go to this number 2 nearest and nearest. So the norm of this functional equals to 2. So third example, very interesting operators, space L2. When I write one space, if I write one space, so we then our operator or function operator acts from this space to the same space. And consider two operators, operators of right shift, right and left shifts. Operator of right shift, A with index R. How it works? It works on the first coordinate we put 0, and all sequence X we shift to the right. Yes, and operator of left shifts take away the first coordinate, and we begin from the second coordinate. Okay. What you can say about the norm? It is very easy examples. If we consider in 2 minutes later, I consider another space more typical for quantum mechanics. But in quantum mechanics, such operators are named rising and annihilating particles. But usually they are considered not in L2, but in two-sided L2, in two-sided L2. But you consider, for example, is it clear that for any x we have equality for right shift, but for the left shift, because we take away the first coordinate, then it is less than the norm of x. So from this, immediately we obtain this answer. But for operator of the left shift, we, for example, take the second, not two, the second basis vector, and of course AL E2 equals E1, yes. So we, with this estimation, from this estimation, we have that the norm not larger than 1, but with this we can conclude that the norm of the left shift is 1. Is it clear?
Yes.
Okay. The fourth example, not fourth example, but usually, but in quantum mechanics, this operator considered in so-called L2Z, two-sided L2. If x belongs to L2Z, it is infinite to both sides. It's from x minus 1, x0, x1, and so on. Yes? And I take brackets in order to mark the center of this sequence. Yes? Because if without these brackets, you can't understand do we shift our sequence or not. For example, operator of the shift to the right acts as following. So we all our sequence move to the right. So on the center place, we take this coordinate. Yes, x0 goes to the right, and from the left we obtain here the corresponding coordinate. And this and the shift to the left. So on the center place, move the first coordinate x1. From the right, come the x2, and x0 go to the left. And with the other coordinate the same. The norm in this space, it's 2 Hilbert space. The norm of x is equals the sum xk square, the square root, but k from minus infinity to infinity. And the scalar product is xk yk, k from minus infinity to infinity. Usually this operator in quantum mechanics two-sided, so-called discrete operator, Schrödinger operator, can be described with the help of this operator. And I think it is a very easy problem. You see that these operators do not change the norm because it is two-sided, so all coordinates preserved. So it's so-called, it is an example of unitary operator. It is R and shift left. It's preserved the norm for any x. So the norm of this operator, as for any unitary operator, the norm equals to 1. Okay. So let's again come back to the functions. Let's G continuous function and fixed. Consider functional f which acts by the formula integral AB fx gx dx for any f from CAB. So it is integration with a fixed function g. Of course, it is a linear function. It is linear function. And let's try to find its norm. Again, first we obtain estimation. First, we obtain estimation for any function f from space of continuous function. The absolute value of result of action. Then standard procedure when we put absolute values inside the integral, it is obvious. And then what we must do, we must obtain this. Yes, we know that the norm in this space is maximum over all interval. So we must take some do something with this integral to obtain this element. Of course, we continue by inequality. We can take away from the integral the maximum value. It is obvious. What candidate we have to the norm, to the answer? What candidate we have to the answer of so conjecture?
The L1 norm of G?
Yes, L1 norm of G, but we only show this estimation that the norm of our functional less or equal of the norm of function G in L1. We show only this. If but we know that for fx equals to signum G, we just obtain the answer.
But it's not continuous.
But it is if function g change sign, then it is not continuous.
But I think we can still approximate it with a continuous function.
If we have countable number of zeros, it is something problem to do it. There exists more easiest procedure. But for example, you're right. For example, you can approximate uniformly our function g by polynomial by Weierstrass theorem. But polynomial has a finite number of zeros. Yes, any polynomial. So of course we can approximate the signum with a continuous function, but I do another. Let epsilon positive. Let's consider function f epsilon of x equals to what? It is just consigned with the g of x if the model g of x not g, but signum g. Is this function is continuous or not? If function g do not change signs, it's of course continuous, yes? But if function g is change the sign, you can see that, for example, what the picture for g. Here I change it on sign, yes, of g, plus 1 and minus 1, signal sign of g. And here this is a sorry, just let this is plus epsilon and minus epsilon. I change function g plus 1 and here minus 1, yes? Oh no, so it is not correct because here I take epsilon and here I take away the epsilon. Is in this situation this function is continuous, yes? Because here for the large values for g, for the large, take it large, we change on the constants with sign, and here we g have the same sign of for these, yes? So it is continuous function. It is continuous. And the norm of f epsilon is
Well, it should be epsilon.
just its function is not if g is not 0, is just epsilon, yes? If g is not 0. So let's modify this function. I take the function nu f tilde epsilon x equals divided on sign of g if g of x and g of x divided on epsilon if g of x less than epsilon. It's just f epsilon divided on epsilon. Then the norm of function f tilde epsilon equals to 1. Yes? Then let's calculate. It's integral over AB, f epsilon tilde of x, g of x dx equals integral on the set such x that gx less than epsilon, and here we have the module g of x, yes? And plus integral for such x, then g of x, here, sorry, such, and here, such. Here we have g square of x divided by epsilon dx. So it is minus here epsilon g of x less than epsilon. Let's take the largest value, then integral x such g of x less than epsilon, and subtract the largest possible value. The largest possible value for g on this set is epsilon, yes? So we take this, and this is not less than this value. Minus epsilon b minus a, and it is tends to the, as you see, to the norm of g of x dx a b. Yes, as epsilon tends to the 0. Is it clear?
Yes.
Okay, another way, I should write another way. You can approximate, first approximate g uniformly by polynomials. By Weierstrass theorem. And second, approximate polynomial, the sign of polynomial by continuous function. And you again show that this is the same.
Excuse me, I have a question.
Yes.
How do we approximate g with polynomials uniformly if we only know that g is an L1, it's not a continuous function?
Not. Let's start previewing it.
Oh, g is continuous. Oh, sorry. Yeah,
Yes.
okay.
If you can consider this functional with g L infinity, but it is more difficult problem.
Okay.
Yes. Function C is so uniformly means that by Weierstrass theorem, of course, from uniformly convergence you have integral convergence. Yes. But polynomial Pn, any polynomial Pn have a finite number of zeros. The problem is we have a countable set of zeros. So, but with this construction of f epsilon, we don't mean this. This integral is estimate easiest. Okay, let's some new examples. Yes. Okay. For example, let's 5. Yes, 5 example. Yeah. Functional f in space C. C small, I remind you, this is space of converging sequences. A, which depends on X. Norm of X is supreme. Functional looks like as follows. The problem, find the norm. Find the norm. Find the norm. Again, simple estimations. When we put the absolute values inside the sum, we, by triangle inequality, immediately obtain the inequality. And then we can take away the maximum, supremum of coordinates. Then we obtain this. It is just the norm of sequence X and C, and this is equals to 1. So conjecture that F, we obtain that the norm less than or equal to 1, but the conjecture that norm equals to 1. But if we analyze this, more analyze not this, but when we analyze the transform from this to this, on what sequence here equality? For what X is equality in this place. Do you see that, of course, the equality will be if we take this element sequence. -1, 1, -1, 1, -1, in order to change this to obtain the same signs for each term. But what is the problem for this sequence?
It's not converging.
It is not in C. Yes, it is not converging. But what we can do? We can do the following play. We can for example, 2n elements not and then finished by zeros. Then the limit, this sequence has the limit, yes, and it lies in C0 and in C. Of course, the norm of this element is 1, and the value of our functional on this sequence equals to what? The sum from k to 1 to n, 1 over 2k. Yes? And of course, it is tends to the 1 as n tends to the infinity. So this gives us the answer that the norm of this functional equals to 1. Okay. Sixth example. Let's consider space. So operator A, F, at point X is an integral with some function k xt, such functions named the kernel of the core of integral operator. Not the kernel, core. Or maybe kernel, maybe a kernel, but I think it's core of integral operator. Let kxt will be continuous with two variables, so it is continuous on the square. And consider this operator A as operator from CAB to, again, CAB, to continuous function. I want to emphasize that the integral operator is continuous analogous of matrix operator. This continuous analog. No, not countable, maybe. It's just analog of matrix operator. Matrix. What I mean? Let's A is matrix. And X is a finite vector. What is, when we multiply A on X and want to find the G coordinate, is just A, E, G, X, G from 1 to N, yes? And now change G on T, A, E, G change to the K, X, T, and sum change to the integral. So you obtain just ft dt, and E change to the X. So, but I have a mistake in previous formula. I take a sum by index G, so it is E's coordinate. Sorry. And now problem, find the norm of A. The answer will be the same as for matrix operator, for multiplication, but where in L infinity, in L infinity norm. And again, we first do some estimations. What estimation? Take any arbitrary continuous function and write the definition of norm. It's maximum over X on the interval AB, the absolute value of the integral. Yes. Then we can do what? Again, put the absolute value inside the integral. Then this is again, I like two norms, two models in his multiplication. So this absolute value of t, of course, less than norm of function f. Yes, because it is value at some point, fixed point, and this is maximum all over points. So we obtain the estimations, the following estimation. Maximum over X AB. So this conjecture that it is it a norm? it is just with if we look on our examples, I want to attract your attention on the example 4 when we consider the function. The function of an integration with the fixed function g. With this example, with the example 4, we can obtain the result for the problem 6. What we can say? I say that there exists, I know that function k is continuous, yes? So this function integral of variable t is continuous function too. AB k xt dt is continuous. Is it clear? Yep. Then there exists such point x0 from the interval AB such that this integral with the fixed point x 0 t dt gives us the maximum yes, because we work on the compact, any continuous of function on compact has its maximum and minimal value. And then consider task 4 with g of t equals continuous function, yes? And then in task 4, we construct f epsilon tilde such that our functional tends to the so what we can do? Take this family from the task 4, right? Take family f epsilon tilde from task 4, but for the function what function? G of t equals k x 0 t. Then we immediately obtain that what we can say about the norm of this operator. From C AB to C AB equals the integral on the second variable, t, second variable, and maximum for first variable. Okay? Is it clear for this?
Yes, thank you.
Okay. I think a lot of examples, yeah. What operators? We consider operator for multiplication of function, yes, in just the lecture. Operator of multiplication of the sequence. Some integral, some functional and continuous functions. Some operators of right and left shift and row 2. Then functional of integration with fixed function. Functional in C, okay. So I think it's enough for today because need to go to the conference. So I write homework. First, show that C star, that's a joint space for the converging, it is L1 plus one element. It is easy to see that it is 2L1. So the adjoint space to converging is just the same, almost the same as adjoint to C0, to the C0. So it is again isometric isomorphism. So show that for any function f, the one-to-one correspondence to y and element alpha, where y lies in L1, alpha lies in from complex numbers, and f acts on x equals alpha x0 plus sum x k y k, k from 1 to infinity. So you can have additional sum. You can rewrite it, of course, in the form x0 y0. Oh, sorry, y0. xk yk, xk yk, but sum from the 0 to infinity, changing alpha equals to y0. Yes. And the norm of this functional equals the alpha plus okay, yeah. Second, let's consider, for example, L3, functional fx equals the sum xk. I think what to put here, in what power. Oh, just find the norm. Find the norm. Third, let's consider C minus 1, 1. It is functional, yes, of course. And again, functional. I write in a simple way. Again, find the norm. The fourth problem. Consider integral operator. Integral operator. We investigate this operator from continuous function to continuous function. A, kxt is continuous function on the square, and consider this operator from L1 AB to CAB. Find the norm. B function again continuous in two variables, and consider this operator from L1 to L1. Oh, sorry, let's first L1 from L1 to L1. And then B, it's more, you will see that it's more logical in this order, in CAB. And again, find the norm. ABC, KXT from L2 AB, and consider this operator A. So here, I correct this index, it's L1. And consider now this operator from L2 AB to L2 AB. And here just, do you see the difference, yes, of the questions? In C, only obtain the inequality, to show it on the boundaries. You have no methods to find the correct, the precise value of the norm. So in AB, just find the precise value of the norm, and in C, obtain the estimation. And 5, operator AF of X is the integration operator from 0 to X ft dt. A in C01 one space, so it's from this space to the same space. Find the norm. And B in L2 01 try to find estimation. Try to find the most precise estimations, but we have no just later we obtain the theorem with the help of which we find the precise value for the norm. But just now try to find the precise estimations.